Well, hopefully other people show up soon. Um, I'm going back to separable equations. So the beginning of chapter 2 is a reminder. When I had derivative of x is number x, I could separate, integrate, solve, and I got an exponential equation. So I remember doing this. It wasn't particularly ugly. It was a nice, straightforward process. But really, we were writing that same idea in a matrix equation. The homework you just gave me is solving crap like this, right? So is there a way that I could write Rx as this? I need some constants in there, right? C1 times the first vector, C2 times the second vector, all that crap. If I make the first vector, oh no, if I make the first vector just want to be multiplied by a number, then I need to put that C on the right so that I would have C1 times the first, C2 times the second, C3 times the third. That would make it work right. And then I could do this like this. But what the hell is e to a matrix? Ah, but, I don't know how to take a matrix as a power of E. I do know how to multiply matrices. I know how to add matrices. I know how to do a lot of matrix arithmetic. How the hell do I do E to a matrix? I don't. I multiply and add matrices. So how can I write E to the stuff as multiplying and adding stuff? You know how to do this. You might hate it, but you know how to do this.
Like power algorithms, rules for that stuff, like a on that to something to convert to kind of.
If I use the rules for logarithms, I'm going to have to do a lot of figuring out how to take that E in there, right? But ln is just going to pull that thing down. And that will make it multiply. Add it. Wait a minute. Wait a minute. I didn't do this specific with matrices ever. I did this for numbers. And I didn't just do it for E, I did it for any function. The appropriate way to do this is with a Taylor series. Yep. Every course comes together this semester. Calc 2, analysis. Diffie Q, we're all doing the same thing. We're doing power series, baby. Okay, wait a minute. I did this. I have a power series for e to the x. I know what it is. The power series for e to the x is the sum. N goes from 0 to infinity, x to the n over n factorial. Great. That works for every x. If we go back and do the convergence test, this converges from minus infinity to infinity. This converges for all real numbers. So I'm going to take this expression and define for any square matrix this idea. I'm going to define the power series plugging in AT. But a raised to the 0 power should be 1, so I'll use the identity matrix here. And then I'll have a to the first and t, where I had x, and I'll have a squared t squared. I'll just put the t squared over the 2. A squared's a coefficient, right? And I can just think of this as taking powers of the matrix A, because I can take any matrix you want and raise it to any power I like. And I can write exactly the same summation, n equals 0 to infinity, a to the n, t to the n over n factorial. As long as I remember that a to the 0 is the identity matrix. By the way, this converges to some matrix for all values of t. This converges everywhere from minus infinity to infinity, just like e to the x does. This is why this is without a doubt my absolute favorite Taylor series. And yes, I'm geeky enough to actually have one. Although if I'm being really pedantic, this is a Maclaurin series. It's centered at 0. Big deal. All right, wait a second. If I'm going to take powers of A over and over and over and over and over, I need to know if I can find a pattern for that. Because if I can't, this is going to suck. So let's consider an example. Grab your calculator. Let's put this matrix in as matrix A and start looking at all the powers of A. See if we can come up with a pattern. there is a theorem from linear that if you remember, you can use here. But I don't know if you'll remember it. So let's see if we can find the pattern on our own.
The one stays the same and two doubles.
Uh-huh. Okay, wait a minute. If it doubles every time, I could write this as 1002 squared, couldn't I? For that 4. And here, I can write it 1002 cubed. And here I can write it 1002 to the 4th. Oh, okay. Remember, 1 raised to any power is 1. So I could think of this 1 up here as 1 squared, and this one here is 1 cubed, and this one here is 1 to the 4th. What's a to the nth power? Yep. But 1 to the n is always 1. Technically, I should use a proof by induction to show that this is... It works. But if that's the case, I can now write e to the at. I'm going to take the identity and then a t and a squared t squared over 2 and a cubed t cubed over 3 factorial and a to the 4th t to the 4th over 4 factorial and so on. All right, wait a minute. The identity is the matrix 1, 0, 0, 1. AT is going to be T 0, 0, 2T. AT squared over 2 is T squared over 2, 0, 0. I'm going to write it 2 T squared over 2. I'm not going to cancel. I'm not going to do any simplifying at any point here. That's squared. Let's do the cube. T to the 3rd over 3 factorial, 0, 0, and then 8. Oh, I see. I screwed it up. This 2 should be a 4. I got to write down the right number. Ooh, bad, Dr. Sassmore. Here, that'll be 8 t cubed over 3 factorial, right? But when you add matrices, you add everything in the corresponding positions. So what goes in the upper left? What goes in the upper left is 1 plus t squared over 2 plus t cubed over 3 factorial plus t to the 4th over 4 factorial and so on. What goes in the upper right corner? As will be in the lower left corner. What goes in the lower right? Oh, 1 plus 2t plus 4 t squared over 2 plus 8 t cubed over 3 factorial, and then it should be 16 t to the 4th over 4 factorial, and so on. Right? Now, I just want to look at that lower right for a moment, because that looks up. By comparison to the thing in the upper left, that looks disgusting. Except, here's a t, here's a 2t. Here's t squared, here's 4t squared, right? Isn't that the same as 2t quantity squared? What about the next term? And then here it would be 2t to the 4th over 4. Hey, wait a minute. Whatever this is, This is the same thing with a 2t replacing the t. But I know what this is. We wrote it down less than 10 minutes ago. That's e to the x. Only it's now e to the t. So what's this? Yep. Holy crap.
The same thing, and it'd be like, say there was a one, it'd just be the same thing next to when the zero is, right, the coefficient is there.
No. The reason this worked so bloody well is because of that pattern up there for a to the x, a to the n, right? Because that stayed diagonal. This is a diagonal matrix, and all of its powers are diagonal. As a matter of fact, I can do that in general. If D is diagonal, and that means it looks like 0 everywhere except upper left to lower right, then D raised to any power just raises those numbers. Oh, let me make this a K since I'm already using N. And that means that with a diagonal matrix, e to the dt is e to the d 1t, e to the d 2t, e to the d nnt, but only when my matrix is diagonal. However, big however, in chapter 7 in the linear book, we talk about diagonalizable matrices, a matrix that I can make into a diagonal thing with a transformation, right? If A is diagonalizable, then there exists a matrix P, which is also n by n, so that A is P D P inverse. And there's this really long, lovely looking theorem that says that the columns of P form an orthonormal set of vectors that is a basis for Rn, and that's called orthogonally diagonalizable. And oh my God, it was a real long, ugly time when I last taught it 2 years ago. But then e to the at is p e to the dt p inverse. So if my matrix isn't diagonal, but can be made diagonal, then I can use this trick. But that's gross. Holy moly. It worked. And for diagonal matrices, this is really easy. And that's because the system of equations, the differential equations that would go with the diagonal matrix, each one of them looks like this. So each of my solutions looks like this. And that's why I got e to the t and e to the 2t. Okay. What does this mean in terms of dealing with a differential equation? Well, it turns out that if I take the derivative with respect to t of e to the at, that behaves just like I want it to. I get a e to the at. Which means if I have a differential equation, x prime equals ax, then the solution works. And what's more, I could multiply each and every row by a constant. Sorry, each and every column by a constant. And if I multiplied each and every column by a constant, that would be the same as multiplying by some vector c over here on the right, made up of constants. So if I give you the set of differential equations x equals 1, 0, 0, 2, like that, we're done. I don't even have to deal with the equations. I just know, oh, the solution we'll call this matrix A, and then I want e to the at times constants, which gives me e to the t, 0, 0, e to the 2t times c1, c2. And if you do the matrix multiplication, you get c1 e to the t, 0, c2 e to the 2t. And that's the right answer. Provided I can find the matrix that is the exponential of my coefficient matrix over there. Holy crap. So I've just changed solving a set of differential equations into solving a matrix again. Before it was find the eigenvalue and eigenvectors. Now it's just find this matrix exponential. That's easy by comparison, I think. Here's another example. Let's find e to the at. First thing I need is a squared. No, I got to do the matrix multiplication. I got to do 1, 1, 1, 1, 1, 1, negative 2, negative 2, negative 2 times 1, 1, 1, 1, 1, 1, negative 2, negative 2, negative 2. And when I do this matrix multiplication, something really nice happens. Yes, you should use your technology for this. You should put this matrix in here and then do matrix squared. Reach here for the graphing calculator.
Zeros.
It is all zeros. Oh, wait a minute. That means what's a cubed? And a to the fourth and a to the fifth, and they're all zeros. Hey, there's a term for this. When you find a power that gives you all zeros, if a to the k equals 0 for some k, we call a nilpotent matrix of order k. So this happens to be nilpotent of order 2. I did the first two and everything else is 0. What do I mean by I did the first two? Let's think about e to the at. Remember, e to the at is I plus at plus a squared t squared over 2 plus a cubed t cubed over 3 factorial plus a to the fourth t to the fourth over 4 factorial. Wait a minute. What do you know about all of this? Okay. All of this is all 0. Which means I can compute e to the at directly. E to the at is 1, 1, 1, 1, 1, 1. Whoop. Wait a minute. I got to write down I first. 1, 0, 0, 0, 1, 0, 0, 0, 1 plus a. 1, 1, 1, 1, 1, 1 minus 2 minus 2 minus 2 times t. So I get t plus 1, 1, sorry, that's multiplied by t. T plus 1, t minus 2t minus 2t, 1 minus 2t. Now I want you to imagine that I ask you to solve the following set of differential equations. You need to find 3 eigenvalues and 3 eigenvectors. But now, because I have this exponential right here, I'm done. X equals this matrix times some C1, C2, C3. Which means I can actually write this out. C1 t plus 1 plus C2T plus C3T, C1T, C2T plus 1, C3T, minus 2C1T, minus 2C2T, plus 1 minus 2T, C3. I found all the solutions. I didn't have to find a single eigenvalue. Unless I'm grossly mistaken, I think that the eigenvalues for this problem suck. I think they're repeated eigenvalues. I don't want to do this if I have to do it the long way. I didn't have to. Because this was nilpotent, finding the matrix exponential was straightforward. And it resulted in my solutions being found really easily. Okay, wait a second. Wait a second here. Let me go back the stuff you just turned in. We had this fundamental matrix, phi of t, right? And we built this fundamental matrix by finding the eigenvalues, finding the solution, and then putting all of that together, right? And it was not trivial. It was not easy. But then we were able to use it. I called the fundamental matrix, I called it phi, right? The textbook is going to use a different letter right now. We're going to find psi of t. Ooh, pitchfork. Technically, the capital Greek psi has flares and serifs. But I can't draw that to save my ass pretty, so I just keep making it a pitchfork. Psi of t as e to the at. That is a fundamental matrix. That means it's invertible. Its columns become the solution vectors. And that means I can use this in that lovely looking integral equation that we did yesterday, where I had to do the integral of psi of t, f of t for the non-homogeneous solution. I can use this matrix. I can use e to the at. This works. But computing a power series over and over and over is just what I love to do with my spare time. Isn't it your favorite thing to do? I think I'd rather hit myself in the head with a brick. Unless I can recognize those power series when I get them and say, oh, that's e to the 2t because this one was e to the t. And I know those power series. And I've got all these power series memorized, right? I have one power series memorized. You've seen it today. The rest of them I have to work out. How can I make this easier? If this is the solution to my differential equation with some initial condition. I might as well make it the identity. So I'll say, x1 of 0 is 1, x2 of 0 is 1. That makes my life easier. Then I can try Laplace transforming this. Wait a second. Wait a second over here. This is a derivative. When I apply the Laplace transform, this is a first order differential equation. When I apply the Laplace transform, I get S times the initial condition minus the Laplace transform of X. Now, I don't know what the Laplace transform of X is yet. And on the other side, I have AX. Well, but I did the Laplace transform. A is a coefficient. Hmm. Oh, did I write that correctly? Did I write that correctly? I think I wrote this backwards. Grab your Laplace transform handout. I think I wrote this backwards. Laplace transform of a derivative. It's S times the Laplace transform minus the initial condition, right? I had them backwards. So let's rearrange. I rearrange and I get S Lx minus A Lx equals x of 0, but we set up here that x of 0 is the identity. Hey, wait a second. I can factor an L of x out of this. S times the identity minus A times L of x is the identity. Hey, I have two matrices that are multiplied together, and I get the identity. That makes them inverses to each other. So if I want to solve L of x is Si minus A inverse. And then I use the inverse Laplace transform here. And that'll give me the e to the at, because this is our solution, x equals e to the at. So when I undo this Laplace transform, I should get x equals the inverse Laplace transform of Si minus A inverse. And that will be e to the at. There's a faster way to find the matrix exponential if I can't find a pattern. So this is my cheat, Hayden, because unless the pattern works out to be really, really nice, I'm in deep trouble trying to find that matrix exponential. But now, here's a better way to do it. Grab your calculators. Here's a matrix. A equals 4, 3, -4, -4. I would like you to take this matrix and raise it to the second, , 3rd, 4th power. 4, 3, -4, -4. I would like you to take this matrix and raise it to the second, 3rd, 4th power. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4. 4, 3, -4, -4 So I start with A. When I square it, raise it to the third power, fourth power. I'm not seeing a nice pattern, are you? This is gross. So let's think about this idea. If I want to find e to the at, I'm going to write out si minus a. That would be s minus 4 minus 3, 4, s plus 4. Just like I was trying to find eigenvectors and eigenvalues, only instead of writing lambda, I wrote s. I'm okay with that. I'm starting the same way. Let's do the inverse of this. What is si minus a inverse? Oh, thank God it's a 2 by 2. I can use that pattern. So the inverse of this matrix is 1 over AD minus BC times, you switch A and D and change the sign of B and C. So I get S plus 4, S minus 4, 3, negative 4. Multiply this crap out on the bottom here. What do I get in the denominator of this fraction? Which would be S minus 2, S plus 2, right? Which means this matrix is S plus 4 over S minus 2, S plus 2. This is 3 over S minus 2, S plus 2. This is negative 4 over S minus 2, S plus 2. And this is S minus 4 over S minus 2, S plus 2. That's the Laplace transform of the matrix I want, which really means I now have to do 4 inverse Laplace transforms. You know the downside of doing 4 inverse Laplace transforms here? I can do partial fractions 4 bloody times. That's okay. I'm going to cheat. I'm going to go to my technology. I'm going to do the Laplace transforms on Wolfram Alpha or Desmos or some other computational engine at this point. I'm going to cheat. I did these already. But you have your Laplace transform sheet up, right? You were just looking at it on your computer. I know what to do with the inverse Laplace transform of this. One over S minus two. What's the inverse Laplace transform of that? That's the S plus two is e to the negative two t, and the S minus two. So I'm going to get negative 1/2 e to the negative 2t plus 3/2 e to the 2t, negative 3/4 e to the negative 2t plus 3/4 e to the 2t, 1 e to the negative 2t minus 1 e to the 2t, and then I'm going to get 3/2 e to the minus 2t minus 1/2 e to the 2t. Which means if I asked you to solve the differential equation with this matrix in it, instead of finding eigenvalues and eigenvectors, that's your fundamental matrix. Now, this is a longer, nastier procedure than you are probably going to want to do for a 2x2. Because for a 2x2, I can find eigenvalues and eigenvectors using a quadratic. That's nice and easy. For a 3x3 or a 4x4 or something more complicated, I really don't like doing the eigenvalue eigenvector stuff. It's gross. This actually makes it easier. If you put a C1 here and a C2 here, and you multiply and simplify, you will get the same sort of number, vector, e to the 2t, e to the minus 2t, the exact same kind of solution we got the other way. But this process is applicable to much larger systems and is therefore useful. It is computationally intense and is easy to program. That's why if I were really stuck solving one of these giant problems that was gross and disgusting like that, I'm going to run over to Wolfram and say, do this. My calculator will not do a matrix as a power of E, but it can do power series for me, which means it can do power series with a matrix for me. I can make this work. Questions? This is not on the exam. But I will see you on Monday for said exam. And I hope you have a wonderful weekend. And if you have your homework,